Well, hello there. Welcome to my channel. And what I'm going to do is try and go through this presentation as quickly as reasonable. My first take was an hour and a half, and I'm going to try and reduce that value by a lot. All right, on this chart here is all the equations for the various parameters you need to calculate what the true or real world value should be given STC, a temperature coefficient, and a temperature of the solar panel or solar cell. All right, VOC is strictly a function of temperature. P max is a function of temperature and energy. I should have changed that to a G, and that should have been changed to a G. Anyway, there's another video already posted where I went through this and did some sample calculations and things. T cell is the panel temperature, and I'm using this is the NOC equation, nominal operating temperature equation, where you take T air in degrees C and you calculate what this solar panel temperature is. The reference for the NOC is 48 degrees C. When making real-world solar panel performance estimates, always adjust or correct for temperature first, then correct for irradiance. Percent over 100 is just turns a percentage into a real number for implementing into a spreadsheet or a calculator. Okay. And these are my results. I start off with an air temperature ranging from minus 14 to 120 degrees F Fahrenheit. First thing I do is I calculate a air temperature in degrees C, because that's what the NOC equation wants. I've estimated a 500 watt per meter squared sun power at solar noon around December 21st, the winter solstice in the northern hemisphere. And 1,000 watts per meter squared for a high temperature case. The gray line indicates my low temperature threshold, where I have memory of the temperature being that cold, and the gray line down here is my high temperature case, where I remember the temperature being that high. This column here is the implementation of the NOC equation, and taking these two values, the sun power and the cell temperature, I calculate the panel output power. And for the open circuit voltage, I just take the temperature correction for the panel temperature given an air temperature using the NOC method, and that's the only thing that matters here. So I've established a lower or cold boundary condition and a high temperature boundary condition for what my solar panel should do. This 750 is basically a guess, and this 900 is basically a guess at this time. I haven't gone and researched what a reasonable value there would be, but it's kind of what I think it should be, given other things I've seen. All right. Next chart. Now I'm going to just flash this up here, do a quick screenshot. This is my STC values. These are my temperature coefficients as given to me by my manufacturer. This is a range of values and the units I actually use. I translated millivolts per degree Kelvin to degrees C. And I could do that because this is being multiplied by a temperature difference, or a delta of 1 degree C is equal to delta 1 degree K. All right. I've seen in the literature that the knock reference temperature, or knock reference energy power from the sun is 800 watts per meter squared. I've also seen it as 80 watts per meter, milliwatts per centimeter squared. These two numbers represent the same power level from the sun in the knock equation. The difference is units. A number without a unit is pretty useless. All right, and how do I get there? Next slide. I'm going to flash this up here. There's an alternative method for calculating the solar panel temperature based on clearance. I don't know how good this estimate is. If you're diagnosing a solar panel, just measure it. That's the best answer you're ever going to get. These are the knock air to panel temperature, cell temperature. All right, and I'm going to leave that. Next one. Now, if you need to estimate solar power, G, or the solar irradiance, the best website you go to is this right here. It's published by the United States National Renewable Energy Laboratory, and it's an irradiance database based on measurements and instruments. Okay, this means that these plots will have weather in the equation. All right, Elizabeth City is a town, university, 2 degrees south latitude from me, and that's the, using historical data, they've already had these plots printed out and ready to use. This peak is for June, or the summer solstice, and it's showing that I should expect 1,000 watts per meter squared plus a little bit. For winter, the winter solstice, December 21st or so in the northern hemisphere, I'm only getting a peak value of 500, and I can't really tell where the direct energy line versus the indirect energy line occurs. Okay, next. On this slide, this is a historical reference of a calendar for the month of December 2013, and I'm using it to see how many good days with the red hearts of solar collecting activity I could conduct, and how those are harvest days. Those are good harvest days. A orange heart with a gray cloud is a partial harvest day. Gray clouds is I'm not getting much of anything out of the sun. I got 4 days in a row, and if I go from this point to that point, December 4th to December 10th, that's 7 days of where my ability to harvest from the sun is pretty low, and I'm going to need an alternative energy source to my solar system for those days. All right, that's basically it.